Welcome everyone. This is the fifth webinar of our webinar series. I'm also pleased to welcome you to this series for 2024. My name is Rob Bertels. I'm an instructor with the Water and Wastewater Technology program at Thompson Rivers University, and I also work with a team of experts on the Online Health Center for BC Small Water Systems. Before we begin, I'd like to acknowledge the Thompson Rivers University campuses are on the traditional lands of the Kamloops Secwepemc, which is the Kamloops campus, and the Tukluk, which is the Williams Lake campus, and the Secwepemc Uluk, which is the traditional unceded territories of the Secwepemc. Thompson Rivers University, with their partners, host an annual webinar series and courses dedicated to providing technical information, resources, and tools for small water system owners, operators, and Indigenous water system owners on issues of treatment, regulation, operation, maintenance, and water quality monitoring. The Online Health Center strives to assist all small water systems in BC to implement a multi-barrier approach to drinking water so systems can provide consistent, safe drinking water to their communities. The webinars are scheduled every 2 months in 2024 and are offered free of charge. For attendees who are EOCP certified operators, each webinar counts as 0.1 CEUs towards your certificate. A certificate of completion will be issued to webinar participants that they can submit to the EOCP. We have a 1-hour presentation followed by half-an-hour question period. During the presentation, if any questions arise, please jot them down in the questions section, and we will be making our way through those questions so we can try and address them. In speaking to Grant prior to this presentation, Grant's our presenter, but in speaking to Grant prior to the presentation, he said that he will try and actually address some of your questions during his presentation. He doesn't mind answering questions. Today, our webinar focuses on troubleshooting small water treatment system processes. You'll learn about some of the most common troubleshooting procedures that you can use to problem solve your small water system treatment plant. We'll focus on common problems associated with UV and chlorine disinfection systems and common pre-treatment systems like water softeners and backwash filters. Our presenter is none other than Grant Roberts, who I just mentioned. Grant has been involved in water treatment in the water treatment industry for 20 years, specializing in small water systems and UV disinfection. He is a co-founder and currently serves as CEO of Home Plus Products Incorporated, a Kamloops-based wholesale distributor of water treatment products. He has a Bachelor's of Business Administration from Simon Fraser University and is an accredited Canadian Water Quality Association as a certified water technician. He has worked extensively with public health authorities and other stakeholders in Western Canada to promote best practices in the application of water treatment technology for small communities and other regulatory applications. He has been a guest speaker in a variety of conferences and events for Interior Health, Vancouver Coastal Health Authority, Island Health Authority, Alberta Health Services, the Canadian Water Quality Association, and the Small Water Users Association of BC, and the BC Institute of Technology. He currently serves as on the Education Committee for the Canadian Water Quality Association. But just prior to Grant's presentation, I'm going to pass the screen over to Natasha so she can provide us with an important update to our website. So Natasha, I'm going to pass this baton over to you.
Thanks, Rob.
Unfortunately there, Natasha, I don't see you down as one of the presenters here.
There are a lot of presenters in here, aren't there?
There certainly are.
Well, maybe I can change presenters. I am. I'm logged in as a small water system. As the small water systems account. Can I just take the presentation? Sure can. I'm going to take it from you. Sorry.
Okay, that's all right.
There we go. Okay, hi everyone. We're having a little advertising break here. The small water the Center for Online Health for Small Water Systems working really hard for the last months and months to create a marketplace for small water operators. And we are really excited to announce that we have launched our marketplace. You'll find it on the website under the Operators Hub. The very first link on the left is the marketplace. So far, we're waiting for people to post, but you can read about the marketplace and learn from our FAQs about it. It is open to anyone who's a small water operator or supply services or products for small water operators in the province of British Columbia. Our marketplace is intended to help you as small water operators access products and services you need in this one place. So you know that it will be your community on this site. It's meant for buying and selling parts and materials or connecting with different services. We do get a number of questions from you guys through email about types of services. So we're hoping that this is going to help answer some of those questions. If you're interested in posting an ad, now again, I forgot to mention, this is free for you to use. It's free to post ads, and it's obviously free to access the ads. If you want to post an ad, you go to the marketplace.smallwatersystems.bc.ca, and I will put this in the chat after. You create an account, and all we need is your email address, give yourself a name, and you need this invitation code. And this is how we make sure that we are going to keep this focused on your audience so that all the postings are useful to you guys. And then you can log in and post your ads. All our ads are vetted for quality, so we'll make sure that what's up there are actually ads for you guys. This is what the marketplace looks like, and you can get to it. I'm going to click back quickly. Oops. Let's go back in here. Apologies for, there we go. I just lost my presentation for a second. There we go. I thought I could go backwards, but I guess I can't. So if you go to the Operators Hub Marketplace and you click there, you will find a link to this website. So you don't have to memorize all of this, but I will put it in the chat. And I will also put this invite code. So if you want to post or you know somebody who has stuff to post, you can share this code with them in order to create their account. And that is all. Thank you, Rob. I'm going to hand it over to Grant now, because he is going to start his presentation.
Okay, good morning, everybody. Thankful that you were all able to make it here, and hopefully I can offer some information today that you'll find useful in dealing with problems that may come up in your water treatment plant. I'm going to try my best to cover some of the most common problems or situations that you may run into, with a bit of a focus on the disinfection side of things, on UV and chlorination. Because pretreatment is so important to both of those functions, it's pretty hard to have a conversation about troubleshooting or addressing problems in UV and chlorination without talking a little bit about pretreatment. So I'll talk a little bit about some of the pretreatment equipment that we commonly see, like water softeners and cartridge filters and so on. And I'm hoping to leave lots of time at the end of our discussion today so that you can ask some specific questions. If we're not able to answer all of those directly in the seminar today, you can post the questions to Natasha, and Natasha will forward them on to me. I'll make sure that they get answered sometime in the next few days for you. And if you want to have a conversation or anything about your specific situation, I'm pretty open to that sort of thing as well. So feel free to reach out. So let's make sure my navigation is all working here. Perfect. I also want to leave you today with a little bit of a methodology for troubleshooting that you can apply to all sorts of problems, whether it be water treatment related or not. but certainly for other water treatment equipment that I might not be addressing in the discussion today. So we're going to start by talking about some kind of general troubleshooting comments, recommendations, etc. Then we'll talk a little bit about cartridge filters, backwashable media filters, softeners, and ion exchange filters. Then we'll get into kind of the meat and potatoes, which will be our UV and chlorination. And as I said, lots of time, hopefully, for questions. It was very interesting putting together this presentation because it forced me to really sit down and think about, where does troubleshooting start? And in my opinion, troubleshooting or the ability to effectively troubleshoot starts before the problem even arises, by being prepared. And being prepared could mean having necessary resources available that may help you troubleshoot. It could be being mentally prepared in terms of your understanding of the equipment that you have and so on. We also need to truly understand the problem that we're looking to solve, and understand the complete problem. In other words, gather as much information as possible about the situation before we dive in. I've seen a lot of cases where troubleshooting is targeting just one symptom of many symptoms that are actually going on within the system. And if we had just started at the beginning by looking at the bigger picture and looking for other symptoms that may be related, it would have given us a better understanding of what we were facing and help us zero in on a solution much faster. I might even be able to give you a couple of examples of that as we go through. Know how your equipment is supposed to work. Fundamentally, it's very hard to solve a problem when you don't know what is a problem and what is not a problem. So we want to understand how our equipment is truly supposed to work. And that doesn't mean, hey, I know it's not supposed to be an alarm, therefore I've got a problem. Really understanding what that equipment is doing and how or what attributes go into making that product work properly. We'll talk a bit about that as it relates to UV and chlorination in particular today. And then my last kind of general recommendation is to be really methodical in how you approach it. And that comes in terms of documentation, and it comes into play in terms of being very thorough and cautious as you're going through the process. I think one of the things that interferes with good troubleshooting a lot of the time is when a problem comes up, when we're not prepared, we end up being somewhat panicked and we're reactive to that panic in a fight or flight kind of way. And we're not always methodically going through our processes, eliminating one procedure or one situation, one potential cause at a time. Sometimes we're taking the shotgun approach and we're trying 10 things all at once, just hoping one of those 10 will be an ultimate solution to our problem. And sometimes that does work, but sometimes the problem with that is that we don't actually end up truly identifying the underlying problem. It was one of those 10 things we tried, but which one? And that which one becomes really important for when the problem comes up again. Because a repetitive problem usually means that there is really an underlying issue that we haven't really addressed. We've put a Band-Aid on it temporarily. So we want to try and be very methodical. So as we're talking about the various troubleshooting procedures and tips today, kind of think back to these 4 key things. And I think you'll find that they all have a tie-in to our suggestions. So here's some other general comments. One of the biggest frustrations that we run into as an equipment provider and designer is a water system coming to us with a genuine problem, but poor details of that problem. And you can help us out and help other service providers out considerably by keeping really good records of the problems that you encounter, including dates and times, what sort of environmental conditions might have been going on at that time. And that might even seem a little bit, unnecessary, but even down to things like weather. We know, for instance, heavy rain can affect watersheds and feed water quality to water treatment plants, for instance, snow melt, even drought, even heat and temperature can play a role with some equipment. So having that data can be very useful. Any test results that were gathered during the problem and outside of that problem, so we can compare changes in water quality. Any kind of data readings that are available, like water pressures, reservoir levels, and those sorts of things. And also keep records of whatever attempts you've made to remedy things. And one thing I'll kind of add to that is also keep a note of what order you did things in. Sometimes we hear back from customers saying, well, I tried this, this, and this. And sometimes that process is really only valid as a test result to us, or might be more predictive of the actual problem if it was done in a particular order. That can be quite true, especially with troubleshooting UV disinfection systems. So we'll talk a little bit about that. On the be prepared side of things, having sample ports and isolation valves throughout your system is very handy for enabling us in troubleshooting to grab samples before and after each piece of equipment. It can help us determine where the root of a problem is occurring. Isolation valves that might allow you to shut off water to a particular aspect of the plant. And I'm going to use the word bypass carefully here. When I say bypass, this can be useful sometimes to temporarily bypass, say, a turbidity filter to determine whether or not we have a pressure loss there. So isolation valves might be appropriate to bypass certain treatment processes, but keep in mind that that will generally not be permissible to bypass any form of disinfection process or a process designed to remove a health-oriented contaminant like arsenic or uranium or something like that. So isolation valves that allow us to bypass a piece of equipment temporarily that's not related to health protection. Obviously, be aware of changes to feed water quality and how that might affect your treatment processes, and seasonality will be a very big one there. So don't be too surprised, for instance, if you see heightened turbidity during spring freshet, and that may have an impact on your equipment. I kind of mentioned this above is, the order of things is important when we're troubleshooting, but so is testing one thing at a time. don't do that shotgun approach. Ideally, I mean, there may be instances where you have no choice, but ideally we want to test one thing at a time. That's that methodical process. It really helps us identify key issues, and that is especially true when problems are caused by a combination of factors. And we will talk about a couple of examples of that, but one I can give you right now is, say, for instance, you have a UV intensity alarm saying that your UV dose is dropping below a safe level. That could be a combination of having an old, weak lamp that's kind of on its last few months, poor feed water quality, and a degraded, older UV sensor that's also starting to fail. Sometimes replacing one of those or fixing one of those problems might be enough to get you out of your immediate alarm condition, but it hasn't truly addressed all of the factors. So you're setting yourself up for an inevitable troubleshooting job again in the near future as one of those other things becomes more severe. Test, and test more if you have the ability to do it. And specifically, make sure you get water samples while the problem is occurring. So, we have instances where, quite commonly in water treatment plants where you get intermittent problems, intermittent poor water quality, intermittent alarms, that sort of thing. And you grab a sample the next day and the problem's gone. So we look at the water test result and everything looks normal. We want to try and grab a sample right during that problem event, and potentially from multiple different sample ports within the system. It really goes a long way to identifying intermittent issues. Have the things you need on hand to do your testing, and have the things you need on hand to do repairs. Some basic repair and maintenance parts that should be available on hand immediately that can assist with troubleshooting. You replace a part, does the problem go away? Well, that's a really good troubleshooting procedure to see if you've got that particular issue. Also on the topic of being prepared, ensure you have operating manuals available. Lots of them have very, very good troubleshooting guides in them that can help you navigate through the troubleshooting procedures for each specific piece of equipment in your system. Certainly have your emergency response plans available, and make sure that those contain some guides to common troubleshooting procedures, especially if you have a lot of turnover or you have a substitute operator stepping in who's less familiar with your equipment. Having that information available to them goes a long way to getting a quick resolution. They know where to go to get some extra help. And speaking of extra help, you can get help from your peers, other water systems, and there's some resources in the online help center to allow you to ask questions of your peers and of course of the administrators of the system. So great resource there. Vendors, manufacturers, engineers, and specialists, and your drinking water officer as well. Your drinking water officer runs into all sorts of scenarios, and if they don't have an answer that might help point you in the right direction, they may have a contact that certainly can. So keep all of these things in mind as we go through our specific procedures, and you'll see that they kind of all tie into this preamble here. Okay, so I'm not going to spend a lot of time on our filter cartridges and backwashable media filters and so on, but I wanted to mention a couple of things that might help you zero in on some specific common problems that you might see in that area. So one of the biggest things that will come up in terms of a problem is a decline in performance usually kind of onset gradually, and or loss of pressure. And on the preparation side of things, one of the things you can do is any equipment that's designed to remove particulates from the water, so backwashable media filters like Nexsand or Turbidex or Filterag, iron filters, and certainly all of your cartridge filters. You should have a pressure gauge before and after each one. As you start to experience pressure loss, you should be able to read those gauges and quickly determine which step in that process is causing the pressure loss, or potentially it's just a combination of multiple all starting to hit their peak contaminant loading, and in the case of a cartridge needing to be replaced or a media filter needing to be backwashed. We should always consider changes in our water conditions that may relate to the onset of that problem. So heavy rains and snowmelt would be significant ones. We may not want to just solve the problem for today by, say, initiating a backwash on our media filter. That'll solve the problem today, but we might also, if we know we're in the middle of snowmelt season and this is going to be going on for a few weeks, we might also want to make a small adjustment, at least temporarily for the next few weeks, to our backwash frequency. That way you won't have the same problem 2 days from now. So we should also consider whether or not our cartridges or our media life, in the case of a backwashable media filter, might be getting close to its life. Most of these have very long lives, other than cartridges, of course. They can be relatively short, and I would say if you're running into a problem where you're going through cartridges really rapidly, days or weeks rather than months, it may be time to talk to a designer or an engineer or a vendor about other options that might be better for your water system to eliminate those problems. There's some quite cost-effective options coming available for small water systems that can really reduce the frequency of cartridge changes and therefore improve the economics of that problem. Water temperature in the summer is starting to pose some additional problems for us, both in creating more algae blooms, but also in reducing the effectiveness of backwashing of media filters. So this would be true for, again, like Nexsand and Turbidex and other turbidity reduction medias, and also iron filters. As the water temperature increases, the water density drops, and it actually takes more flow rate to achieve the same level of backwash. So we are starting to see some problems on lake water sources in particular, where the water warms up quite a bit in the summer and the effectiveness of backwash decreases. So, something to definitely keep your eyes on. Sometimes a failed backwash can be a part of the problem. Power outages are usually the cause of that sort of issue. If you're subject to repeated power outages in your area, putting your media filters on an uninterruptible power supply, kind of like a computer backup power system, is a very cost-effective way of preventing that issue. You can do the same thing with your chlorine pumps and UV disinfection systems. Especially if you're on a gravity-fed system where you're not relying on pumps during power outages to move water, you can keep your water treatment plants running quite effectively that way. And one of the other problems I wanted to mention that's quite common is, and it's related to kind of a missed maintenance opportunity. Probably a good way of describing it is inside these control valves, essentially you have a little motor that's connected to a timer. The timer decides when a backwash is supposed to occur, and the motor moves a little piston. The piston opens up ports that are sealed by what we typically refer to as a seal and spacer stack. And all of those are wear and tear parts. They definitely do not last forever. And in most cases, you're replacing them every 2 or 3 years. But one of the most common signs of a problem or the start of a failure of one of those components is that water will leak to drain when you're in normal service mode. So if you hear water trickling to your drain, that's a very common issue, and you should service your seal and spacers and piston. Not a bad idea to have those parts on hand so that you don't experience any downtime, especially if you have older systems where parts may be more time consuming to obtain. Oh, there it goes. Okay. Softeners and ion exchange often form part of our pre-treatment. Water softeners are typically used to remove hardness minerals like calcium and magnesium from the water. And sometimes they're also used to remove lower levels of iron and manganese. Iron and manganese in particular cause problems for UV disinfection and chlorination. And certainly hard water can cause some issues with UV disinfection as well. So it's a very important part of our pre-treatment. Ion exchange filters are basically identical to water softeners, except the resin has the opposite electrostatic charge on it. So instead of attracting positively charged contaminants, they attract negatively charged contaminants. And in most small water systems, that would be used to remove natural organic matter and tannins from the water. Tannins and organics typically are responsible for that yellow to brown tea color that we see in a lot of surface waters. Those tannins and natural organics are also very problematic to our UV disinfection and also for our chlorination. So I kind of lumped these all together because they're closely related and the equipment is largely the same. I have a little diagram here of a typical water softener or ion exchange filter, just so I could show you and explain to you in very basic terms how they work. Because like I said at the beginning, understanding how a system works is really important to understanding how to troubleshoot it. Because you need to be able to identify what's normal and what's not normal. So most of the problems in ion exchange can be traced to a loss of capacity in the resin. It's simply failing and it no longer has the capacity that it used to have originally. And at some point that capacity will get to the stage at which it's no longer cost effective or productive to continue to run it, and it simply needs to be replaced. Other times, there's something in the process that's preventing the creation of a brine solution. I'll explain what that is in a minute. That is effectively strong enough to do its job. And the last problem is something is preventing that brine from moving correctly through the system. So in the diagram here, we have number one at the top is the control valve. And again, that's just a fancy timer. Most often, they will also have a built-in or external water meter that counts the amount of water being processed by the system, which is really important. We have the media, which is number 5. That's the magic. That's the workhorse that's doing all the work. That media has a certain amount of capacity to remove contaminants. Once that capacity is used up, we need to regenerate the media to restore the capacity back as close to maximum capacity as possible. And we do that with salt brine. So on the right there, we have a brine tank that we fill with salt and water. And the water dissolves some of the salt up to the point of being completely saturated. And we draw that salt water out of the tank, out of the brine tank, and into the media tank during our regeneration process. That salt brine goes down through the media bed, or in some softeners, up through the media bed, and it restores the capacity of the resin back to normal. We then rinse all of the contaminants and excess brine down the drain. So when we're done, all of that salty brine water should be gone out of the system. We put some more water back in the brine tank so it can make nice new brine for our next regeneration, so it's ready to go for next time. So in very simple terms, that's how a water softener is working. So poor or intermittent performance is probably one of the biggest problems that will come up, and that will be reflected in, for instance, some of your downstream equipment. So for instance, if we failed to remove iron with our water softener, that would increase our chlorine demand, which might cause our chlorine residual level to drop. Or if we're using an ion exchange filter to remove natural organic matter, and we have an intermittent performance problem, we could have a UV intensity alarm because the organics absorb UV light and cause our UV intensity to drop. So it's really important that we be on the lookout for problems related to the performance of our ion exchange and softeners. So one of our first considerations is, have our feed water conditions changed? Ideally, if you have test equipment on hand, you can do a quick test, compare that to your background levels, and see if any adjustments are needed. One of the most important programming parameters on a water softener is, what is my hardness level, or what is my organics level? And if your organics levels are, your hardness levels are fluctuating and you're not making programming adjustments, you're going to have intermittent performance issues. The media does not last forever. You can apply resin cleaners, for softeners, Res Care, Res Up, Iron Out are all good examples. You can buy water softener salt that has resin cleaners built in. Those can help keep your capacity as close to 100% as possible, but there will always be a natural decline as time goes on. One of the troubleshooting procedures that's really handy that you can do, especially if you're noticing that immediately after you regenerate your equipment, it works really well, but it gradually declines and performs very poorly kind of late in its service cycle before its next regeneration, is you can get a water sample every day over that service cycle and look at the hardness result or look at the organics result. And you can find out, for instance, that, well, I was only able to last 4 days, but I'm regenerating every 7 days. Well, you're going to have to adjust your programming to reflect that natural design or decline in capacity over the life of the system, to reflect that loss of capacity, to ensure you have performance that is effective on an ongoing basis. And of course, if that cycle gets so short, at some point it's just going to make sense to replace that resin with new media. One of the most important things you can do as a quick test in a water softener, it is to disconnect the brine line. So I'm going to go back a step here. So the brine line is the little black line that's running between the control valve at the top down to the brine tank on the bottom right. And that's how brine moves from the brine tank into the softener, and it's how water is added back to the brine tank when we're done the process, so we can create new brine for next time. We want to look at the movement of water through that line and movement of brine. So if we disconnect the line from the brine tank and we put our water softener or ion exchange filter into the regeneration mode and skip through to the brine draw mode, we should literally be able to feel suction on the end of that line if we put our finger on the end of the line. Or grab a glass of water and stick the tube in that glass of water, and we should literally be able to watch it sucking water out of the glass. If it's not sucking water out of the glass, you have a problem in your control valve. If it is sucking water out of the glass, but you're not getting a good regeneration, you probably have a fault within the components in your brine tank. So it's a really quick way of determining where a problem might be. So very, very, very handy. If you have a problem in the control valve, most often it's related to clogged injectors and the injector screen. The injector is actually what creates the suction. So if you're not getting suction, either that injector's plugged, in which case you can clean it or replace it. They're usually, under $10. And there's a little screen that is meant to keep debris out of that injector. Quite often that little screen is just plugged up with debris as well. So you can either clean or replace that, and that'll usually restore your suction. So a couple of quick, easy parts to look for there. It takes time to make good brine as well. So if you've got a case where you've got a cycle that is very, very short, so you're running, say, twin water softeners, but they're running for 2 hours and then going into regeneration, then flipping over to your other softener, just be aware that you're never going to effectively regenerate because you haven't given enough time for the water to dissolve the salt. So you're using a really weak brine. Couple of other things to do quick inspections and check is, clean your brine tank components. At the bottom of that gray tube at the bottom of the brine tank there's a little check ball in there. It's really important that that check ball be moving and not be stuck. So check to make sure that that's operating correctly. Check to make sure the safety float's operating correctly. Make sure the salt is actually falling all the way down to the bottom of the tank. We sometimes see what we refer to as salt bridging, which, like its name suggests, it's like a bridge of salt at the top of the brine tank, and then there's a big hollow cavity underneath that, preventing the salt from actually touching the water at the bottom of the brine tank. There's usually a flow meter, like I said, associated with this type of equipment. Make sure that flow meter is clean as well and operating correctly. Most softeners on the screen, when you're running water, you can actually see a countdown of the number of gallons remaining until the next regeneration cycle. If you're running water and you don't see that counting down, you probably have a problem with that flow meter. So you can take a look at that. Just going to mention a couple of small other things to watch for, and then we're going to move on to UV. A brine tank with too much water in it is usually a sign that we're not drawing brine properly. So do that brine draw test that I talked about earlier. Most likely you have a clogged injector or injector screen and you're not getting that brine suction. You might also have a kink in your brine line itself, or the brine line might be clogged. Those are all very, very inexpensive things to check and replace. So definitely worth doing. Too much water in the brine tank, if it's higher than what it normally is usually a sign that some sort of problem is starting. So when you go to add salt to your brine tank, if the water level looks unusually high, you probably have an issue there. Rarely, if there's a power outage, you may lose some programming, and your cycle times may have been affected as well. So anytime you have unusual things going on, you should be aware of your normal cycle times, and you can check those to make sure that they're as they're supposed to be. Changes in salt consumption are also good indicators that you have a problem. Sometimes a change in salt consumption will be just strictly tied to a change in water use within your facility. That's normal, but if your water use is as it usually is and you're seeing increased or decreased salt consumption, you should proactively start looking to see why that's occurring and hopefully address something before it becomes a bigger problem. Salty tasting water left after regeneration is usually due to an injector or injector screen clogging issue as well. So get familiar with that injector screen and the injector, know how to clean them and access them. They're usually very, very easy. It's minutes to do. Very good proactive maintenance. Okay.
Grant, could I just interrupt for a minute about some questions?
Yeah, I can't hear you very well, Natasha.
Oh.
I can hear that you're speaking, but I can barely hear you.
Can you hear me now?
It's still the same, unfortunately.
Okay. There's some questions.
Hang on, I'm going to really crank up my speaker here and see if that helps. Okay, try that again.
Some people ask some questions about water softening.
Okay.
The first one is in the question box about sodium levels being too high.
Okay, good question. So water softening and ion exchange is exactly that. It's an exchange process. One of the drawbacks of water softening and treating organics with ion exchange is that when we take out the bad thing, so for instance, we remove iron or we remove hardness, we add back something else. And in the case of a water softener, we add some sodium to the water. In the case of a organics or tannin filter, we add some chloride to the water. And it's quite predictable, in fact, very predictable, how much sodium and how much chloride we would add to the water in that process. And particularly in the cases where the water is really hard or there's naturally high levels of sodium already present, it is possible with a water softener to add enough sodium to the water to put you over the drinking water standard for sodium. And sodium is very challenging to actually remove, and it does impart a little bit of what most people would refer to as a salty taste to the water. There aren't a lot of alternatives available to prevent this. The only what I would refer to as credible alternative on the market is what we would refer to as a template assisted crystallization, or TAC filter. And they can't be used where iron or manganese is present, and they would only be used where hardness is present as a scale prevention treatment. They don't actually remove the hardness, but what they do is cause the hardness to change form. So instead of in a dissolved calcium or magnesium form that would subsequently form mineral scale in your system, especially when the water was heated, it causes the formation of a microcrystal, nanometer sized, extremely tiny crystals that are very, very stable, and they stay suspended in solution. They just simply pass through the system without forming scale on any surfaces. That technology is becoming very popular because it doesn't involve a salt brine regeneration. It doesn't involve any water waste. The media lasts generally quite a long time, as long as there's no iron or manganese present. And they are quite effective. They're less effective as your distribution system gets bigger and bigger. So if you're sending the water several kilometers away to the end of the distribution line in your small town, it's not as effective in that sort of scenario as it would be if you were providing water to, a 6-unit RV park or something like that. But that is an alternative, and it does not add sodium to the water, but a conventional water softener absolutely will. Now, sometimes your sodium problem can be related just to that natural exchange process that a water softener does. But sometimes it can also be related to your softener not functioning correctly and leaving excessive amounts of brine solution in the treatment tank at the end of the treatment process, or regeneration process, pardon me. And that would be normally identified by a problem where the taste, saltiness, the increased sodium was only present immediately after a regeneration, because once you start running service water, it'll eventually flush out. But if immediately after a regeneration, you're seeing really high sodium levels, and especially if your TDS level goes higher than what your normal background TDS level, that's total dissolved solids, that's an indicator that your softener is not functioning correctly.
Grant, we have another question here with regards to brine tanks here. So the question is, does a dirty brine tank prevent brine from moving good brine?
It can, yes. So at the bottom, let me go back to my picture here. Oops, not like that. So again, right at the bottom of that brine tank, you see that little gray rectangular looking device. That's an air check valve. And it's there because the second function, or what's normally the second function in a water softener, is our brine draw and slow rinse cycle. And that's where suction is created by the injector. We draw all of the salt water out of the brine tank and into our media tank. And when it runs out of water, that little check valve has a bulb that closes that valve off at the bottom of the brine tank. Otherwise, we would start sucking a whole bunch of air into our system. So if that little check ball gets stuck because of debris in the closed position, it will prevent us from drawing brine properly. And that's more likely to occur as our brine tank gets dirty. Most modern water softening salts, especially the pellet style, are quite clean. They don't contain a lot of impurities, but there are still some impurities that don't dissolve and they will accumulate in the bottom of our brine tank. So we generally recommend preventative maintenance. Clean your brine tank out once a year and check the operation of your safety float, check the operation of that check ball. And all you have to do to check the operation of that check ball is to tilt it back and forth and you'll hear it moving around in there. But if it's not free and moving, then there could be debris in there because it got dirty in the brine tank and we sucked some debris in there. Does that cover that okay?
I think so.
Okay. See, there's some other questions here about cleaning quartz sleeve. I'm going to get to that in just 1 second here. Okay, so let's move on to UV and chlorination, which work hand in hand as part of our multi-barrier approach that we use here in BC for our disinfection processes. And again, it's important to understand how the equipment works in order to understand exactly how we would go about troubleshooting our UV system. So all UV systems operate under much the same principle. Some have many lamps, some have different types of lamps, some have different flow patterns through the chambers, but the intent is all very, very similar. So the heart of the system is an ultraviolet generating lamp, and the UV light emanates out from that lamp, passes through a quartz glass sleeve. In my picture here, the lamp is the yellow thing in the middle. The quartz glass tube is the rectangular box around it, and then between that box and the outer part of the chamber is where the water flows. So the light has to pass through a little bit of air, then it passes through the quartz glass sleeve, then it has to pass through the water and ideally reach the outermost part of the chamber. On the left-hand side, 3/4 of the way up there, I have a little picture to depict a UV intensity monitor. So a sensor that's monitoring the UV light getting to the outside part of the chamber there. And in order for that disinfection to occur, we have to get that UV light to pass through all of those things. So one of the most common problems is that something is blocking or otherwise impeding the UV light from getting where it needs to get to. So that's a very important and very common cause of UV problems. We can sometimes have environmental conditions that reduce UV light output. So a lot of UV systems allow for convection of air across the UV lamp. In between the lamp and the sleeve, there's that space of air, and they'll allow air to convect through that space for cooling purposes. But what happens if the ambient air temperature is like 3 degrees Celsius and we're drawing really cold air in? That can actually cause our UV light output to drop. The lamp becomes less effective. And conversely, if something's interfering with that cooling process, or we're drawing really hot air into the system, as the lamp gets too hot, we can also have problems with output as well. So Environmental conditions can certainly play a role. And then, of course, we can have a problem where the system itself is just not generating UV light of sufficient intensity. So those are really the root of the problems. And if we understand what is involved in each of those processes, we can help troubleshoot the problem. So let's look at a couple of very, very common UV problems and how we might go about looking into those problems, remedying them, and preventing them in the future, hopefully. So lamp failure is something that happens. It is a little bit less common than people think. One of the things that we see is people jumping to the conclusion that because I have a UV problem, my lamp output must be poor, and they jump in there right away and replace their lamp. And you know what? Sometimes that fixes the problem. Sometimes it fixes it because the problem was the lamp. Sometimes it fixes the problem because a brand new lamp has 100% output, close to it, whereas an older lamp might have had 90% output. Now, if you had some other problem going on, boosting that output by 10% or so might have been enough of a boost to get you out of that problem. But you didn't actually really solve the underlying problem. You put a Band-Aid on it because the next time that lamp gets down to 90% again, the same problem is going to occur, and you're probably going to be cycling your lamps a lot more often than you really need to. You'd be better off to solve the actual underlying issue. So we do find that people do replace these probably more than they should or need to, chasing problems that are really something else. But it is important to consider the age of the lamp. If it's most UV lamps have a 9,000 hour or roughly 1 year life. There's some on the market that are 2 years, but if it has a 12-month life and you're at 11 and a half months, and you're starting to get an intensity or a UV alarm issue, you have to give some consideration to it being a lamp. If the lamp's 2 months old, it's probably much less likely to lamp, but it could be. You can inspect the lamp for damage. Often when there is a lamp failure, you will see, just like a fluorescent tube, you'll see blackening at the ends of the UV lamp that can be indicative of a problem. You could see a broken filament in it. There may be some obvious signs of damage. Inspecting the lamp is something you can do very, very quickly. I talked about being prepared. Part of being prepared is to have a spare lamp on hand. If you replace the lamp, does the problem go away? Especially if your system's telling you have a failed lamp as opposed to an intensity problem, it's a pretty good chance you actually do have a failed lamp. Listen to what your system is telling you and use that spare to test and diagnose whether or not that's correct. I've had a few cases where people have replaced the lamp with a brand new one and it doesn't fix the problem, so then they assume that the lamp that they had on the shelf is also bad. And I would beg to suggest that multiple lamps not firing correctly in a system probably means it's not the lamp. So if your new lamp has the same problem, definitely start looking for causes outside of lamps. Some other things that can cause a lamp not to fire at all could be a ballast failure, problem with the power supply, breakers. There are fuses in some of the UV units as well where the fuse will blow and need to be replaced. Could be a problem with the breakers in your main electrical panel. Could be a problem with the electrical outlet, so try a different outlet. And a lot of the UV systems these days have fail-safe mechanisms put in place so that you cannot fire the lamp without the lamp harness properly installed and the lamp inside the chamber. Most of those have some sort of safety switch or reed switch. A reed switch is like a little magnetic switch that when two things are in proximity, it'll activate the switch and allow power to flow to the lamp. Some of the time, those reed switches or those safety switches have actually failed, or they're not properly engaged. So it's not letting you fire the lamp simply because it wouldn't be safe to do so. A lot of the UV system controllers will have some sort of indicator to let you know that that is likely a problem, or point you in the right direction at least. Repeated lamp failures could also be a sign of a failing ballast or bigger equipment problem related to the power supply, especially if that's causing very heavy on-off cycling of the lamp. UV lamps prefer to just turn on and stay on continuously. Most of the wear and tear happens starting and stopping them. So I know there are some water systems that batch process their water. You know, they turn their system on for an hour a day, fill a big reservoir, shut it all off, including their UV system, and then turn it on the next morning and repeat. That's really, really hard on the UV lamps and will often result in premature lamp wear. So that's something to be aware of if you're operating your system in that manner. And probably one of my strictest adherences that has shown a lot of evidence to be a problem in the field is using non-OEM lamps. So OEM basically means use the lamp made by the manufacturer of your UV system. Don't put brand X lamps in brand Z's UV sterilizer. This is really important for a number of reasons. Number one, your safety validations, your third-party validations on that equipment are void, as are your electrical safety certifications in using a lamp that is not made by the original equipment manufacturer. You have no idea what you're getting. You may be getting a fantastic equal lamp, but you very likely are not. You know, a lot of the OEM lamps are made overseas, not nearly to the same standards. They're attractive because they're less costly, of course. So there's an incentive to want to use them. But in our experience, they cause a great deal of problems. The UV output is rarely equivalent. They rarely last as long, and in extreme cases, they actually cause equipment damage. We've seen even fires caused by poor fitting lamp pins and that sort of thing. I'm aware of a small water system on Shuswap Lake that was using non-OEM lamps and caused about $15,000 in damage to their UV equipment doing so. So be very careful where you're buying your lamps and make sure they're genuine OEM lamps so that you know exactly what you're getting. Okay. So the number one problem that we hear about in troubleshooting related to UV systems is related to alarms. I have an alarm where my system has shut down Often a solenoid has closed and won't let me produce any water or send any water out to distribution because the system is saying that it cannot adequately or safely disinfect the water. What do I do? Where do I go? And there's a couple of things that you can do that are quite definitive in eliminating some of the possibilities. So back to my little picture here, we have this sensor on the side of the chamber, and in order for that sensor to say everything is good with my UV system, let's keep producing water, UV light has to get from the lamp through that little pocket of air, through the sleeve, through the water, through the window on the sensor, the little glass screen on the sensor, and then into the sensor itself, where the sensor can capture that reading. So when you have an intensity alarm, something in that process is breaking down. It could be that the UV lamp itself is no longer putting out its proper UV output. As I said, you can consider the age of the lamp, and if it's getting close to its life, it's maybe a little bit more likely to be related to that. If you have a newer lamp, I would probably suspect that it is not that and move on deeper into troubleshooting, because we don't want to just replace the lamp, bump the UV intensity a few percent, narrowly get out of an alarm condition and just set ourselves up to have another alarm in the near future. The next thing you should do, and this should be a part of your regular maintenance anyway, but clean the UV sleeve. Hardness minerals, iron, manganese, natural organics, sometimes biofilm even, like dead bacteria, especially if you have heavy bacterial loads in your raw water, can potentially accumulate on that sleeve, and over time they will reduce the amount of UV light that can pass through the sleeve. I actually have an example in one of my other presentations where I show a UV sleeve that is completely orange. You know, it has about a 32nd of an inch iron deposits built up on it. That UV sleeve, no UV light was getting through it. Clean the sleeve with CLR or Lime Away. Do not use vinegar. Ideally, don't use alcohol. Definitely do not use window cleaners. Some of those things will make the lamp, or pardon me, the sleeve look very, very clean to you visually, but they will leave residues that block UV light. CLR, which I think a lot of people are familiar, calcium lime rust, it's a cleaner you could buy at Canadian Tire or any hardware store, is very, very effective. Also clean the little glass window on the sensor. That little window, if it's got mineral buildup on it, will also block the UV light from reaching the sensor. Once you've done that, you can perform what we refer to as a dry test. Or if you're lucky enough to have a UV transmittance testing machine, and I know not everybody does, but if you do, you can do a UV transmittance test on your water, and again, capture the water, ideally that is literally in the chamber at that moment that you're having an alarm, or at a sample port right beside it, ideally. If your UV transmittance is low, especially below 75%, that's probably the cause of your alarm. The problem is not your UV sterilizer. In fact, your UV sterilizer is doing exactly what it's supposed to do and warning you that I can't treat this water adequately anymore because your pre-treatment is either failing or inadequate. So there's organic matter getting through, that's absorbing the UV light, causing the your dosage to drop, or there's sediment particles in the water that are interfering with the transmission of that UV light. If you don't have the UVT tester, you can still determine, is this water related or is this equipment related, by doing a dry test. As its name suggests, you drain the water out of the UV chamber. We remove water from the equation. Water is not the problem because it's not there. We fire up our UV sterilizer without water in it. We allow 4 or 5 minutes for it to fully warm up. Does the problem go away? If the problem goes away, the problem is most likely your water. If the problem persists, then I would consider more likely that there's an equipment problem. But we've gone a long way here. We've eliminated water or equipment, one or the other, by either doing a UVT test or doing this dry test. Don't run your system for an hour. It's not necessary, and it's actually not that great for your equipment to allow it to run that hot, because it'll run hotter with water in the system. But you can run it for 5 minutes, let it fully warm up. Some UV systems have a display that will tell you also some information about the intensity that's being detected. If you eliminate the water and suddenly you're detecting a lot more UV intensity, and as shown on your display, it's probably your water that's not quite up to standard. So some other things to consider, especially if you have problems repeatedly with intensity issues. Consider whether or not you have temperature management related problems. Is there any other equipment in the room that is causing excessive heat? To a exhaust fan from something blowing right on your UV sterilizer. We had once somebody did a really nice job of insulating all of the pipes in their water treatment room, but they decided to also insulate their water treatment chamber, which allowed no cooling of their chamber, caused everything to overheat, had lots of intensity alarms because the lamp output dropped. Extreme cold can also be an issue. So in the winter, if you're running really low ambient temperatures and suddenly you're getting more and more intensity alarms, you probably need to warm up the air temperature in your treatment room so that your system can run at the ideal operating temperature. Consider the orientation of your chamber. Some manufacturers specify that their chambers can only be installed vertically. That's very important in some systems for temperature management. It also sets the orientation of the intensity sensor though. So when the intensity sensor is mounted on a horizontal chamber and it's on the top of the chamber, it tends to be an area where air pockets or any air passing through the water lines tend to accumulate. That those little air bubbles will interfere with the readings of the sensor. And on the converse side of things, if the sensor is mounted such that it is on the bottom, it becomes a little bit more of an area where debris will settle. So if you have ultra-fine sediments that are passing through your pretreatment and you shut the water off at night, there's no water running, that sediment will tend to settle on the little window of your sensor when it's oriented on the bottom. So give some consideration to your chamber orientation if you're seeing frequent intensity alarms. You can always try installing a new test and, a new lamp and sleeve to see if it makes a difference. Sleeves also do not last forever. If the sleeve is starting to look hazy or has deposits on it that when you clean it remain after the cleaning, that sleeve needs to be replaced. A lot of the manufacturers are even selling lamp sleeve combination kits now, where the sleeve, they're almost giving it away because they really want you to maintain that sleeve. And a fresh, clean sleeve is important, not to be forgotten. We would generally say, 2 to 3 years maximum for most sleeves, and especially true if you have hardness, iron, or manganese, because it will get into the pores of that sleeve. You can't see them, but then, this looks like nice smooth glass to you and I, but if you look at it under an electron microscope, you will see that it's porous and stuff will get in there. If you have a periodic problem, try and also relate it or correlate it to events. Does this happen every time it rains? Does it happen every time my water softener regenerates? Every time my tannin filter regenerates? Every time my iron filter backwashes? This is where your record keeping can be really important, because we can correlate it potentially to intermittent pretreatment failures. And if we don't have good records, that can be very, very hard to identify. And lastly, UV intensity sensors also don't last forever. They do have a life and they can fail. So particularly if you have tried a new lamp, a new sleeve, you've done dry tests, and it's definitely seeming to be equipment related, the next thing to try would typically be replacing the sensor itself. And if you're at 7 or 8 or 9, 10 years on a sensor, that's a pretty decent chance that that sensor is just at the end of its life. They're designed to fail by being more sensitive than a new sensor would be. So they kind of always fail in the safe direction. Be on the lookout for that if your sensors are getting really old. They are considered a wear and tear part. They do not last forever. Sorry, I see that I'm getting a little tight on my time here, and I can stay later for questions and so on if we have them. So we're not going to cut our question opportunity short. Ballast failure is quite rare, but can happen. It's kind of the last thing we go to. Sometimes, like in the ballast pictured here, there'll be lights or indicators on the unit that can help you determine which component may be the problematic item in the system. So sometimes it will indicate a ballast failure or problem. And generally, those indicators are correct. The one thing that I would suggest to always check for before you assume a ballast failure, even if the controller is indicating such, is make sure whatever safety harness or reed switch type of apparatus is on that unit, make sure that is connected properly before assuming that it's a controller, because I have seen cases where it indicates a controller failure, but really it's a connection failure. And certainly if you have a repeated ballast failure, I can virtually guarantee that you have a power supply problem at that location. We most commonly see it in remote areas that are very prone to brownouts or power failures, lots of electrical storms and that sort of thing. Protect that ballast with an uninterruptible power supply and a surge protector, and you might save yourself some expensive controllers. That's definitely something that we see in remote areas, like I said. One thing that is very, very handy is a lot of small water systems run multiple UV units, or they have a redundant backup UV already installed. So, if you have, say, a 50-gallon per minute water system, I would be very hesitant personally to install a single 50-gallon per minute UV sterilizer. I would be much more inclined to install, say, 2 30-gallon per minute, or even better yet, 2 50-gallon per minute units, or 3 20s, or some combination that involves more than one UV sterilizer. That obviously adds resiliency to your system in that you have some redundancy, at least to have partial capacity in the event of a problem. But it also means that you have a duplicate set of every piece of equipment on hand. If both units are in alarm and doing exactly the same sort of alarm condition, or if you have 3 units, all 3 of them, you can strongly suspect that the problem is related to source water quality. It could potentially be related to lack of maintenance, i.e. sleeve cleaning on all 3 units, or both units, or whatever the case may be. But it's probably more likely a water supply issue. If only one of your multiple units is in alarm, you can suspect it's more likely an equipment problem. And you can literally one by one start swapping equipment between your 2 units and use that to identify what component is causing the grief. Now, I would only start swapping components, of course, after I cleaned my sleeve, cleaned my sensor window, and did that proactive maintenance first. But you have all of the components for sure on hand to identify that problem. But switch them one at a time. Don't switch to, you want to, or 3 or 4, you want to do it one at a time till you identify exactly which one the component is. It's as good as having spare parts sitting on the shelf. You've got them already there in service. Okay. All right. So chlorination. I've got a picture here of a typical chlorination system. Obviously, there's variability in how they work and the specific pieces of equipment, but generally we have an injection pump that draws chlorine solution out of a tank, might be controlled by a flow meter so that we can inject the chlorine in an amount proportional to the water flow. So more chlorine when flow rate's higher, less chlorine when flow rate's lower. We might have some sort of mixer, and then the water is generally sent to some sort of contact tank where we give the chlorine time to do its job, because chlorine does not act instantly. While it's doing its job, some of the chlorine is used up interacting with organic matter. Some of the chlorine is used up interacting with iron and manganese. Some is interacted with bacteria and other microorganisms. And coming out the other end is less chlorine than we put in. So what we put in is our total chlorine. What comes out is our residual chlorine. And what is used up is referred to as our chlorine demand. So if the amount of iron or organic matter was to increase, we would have more chlorine demand. And unless we increased the amount of chlorine we were injecting, we would have less residual coming out the other end. Chlorine also dissipates over time. So the strength of our chlorine solution that we're injecting is not a constant. When you mix up a nice batch of chlorine today, and you come back a month from now, if you still have chlorine in your solution tank a month from now, it will not quite be as strong as what you started with. You come back in 6 months and it will be about half as strong. Similarly, if you have an open contact tank and you store water after it's treated for a really long period of time, the chlorine level will dissipate. If you send it down very, very long distribution pipes, the amount of chlorine getting to the end of your distribution line will be lower. You will have some chlorine demand as it interacts with residual contaminants in the distribution line, and you will have some chlorine dissipation and breakdown. So it's important to understand those processes so that we can figure out where things are going wrong. So typically, we're going to have a problem with our chlorine solution strength. We're going to have inconsistent injection or mixing, or we're going to have changes in our chlorine demand. Those are the main things that cause grief for us in chlorination systems. So as I said, chlorine is not all created equally, and nor does it stay equal. So we need to pay attention that when we buy chlorine, we're always buying the same strength. You know, if you buy 12% and put that in your solution tank today, and then next time you buy chlorine, you buy 6% strength, and you put that in your solution tank, you should not expect the same results. Similarly, if you buy a 6-month supply of chlorine and the chlorine you use today is going to be nice and fresh, there's a reason that is bold in red and underlined. Fresh is really important. We try and shoot for chlorine that has been purchased within the last month, because don't forget, it might have sat on the store shelf for some time as well. If you have problems with one supplier, switch suppliers to somebody who has good, fresh chlorine. It definitely degrades and will not be the same as time goes on. It doesn't mean you can't use it as it degrades a little bit, but it means you might have to inject a higher quantity of chlorine solution to achieve the same result. And this I can't emphasize enough either. It probably should be bold, red, and underlined as well, is dilute it. A lot of systems would greatly benefit from dilution who are not doing it today, meaning that we don't put 12% chlorine directly into our solution tank and inject that. This is especially true for small systems running flows of, say less than 30 gallons per minute. Dilution is really important to create mixing. And it's even more important if you don't have a static mixer or a large reservoir where natural mixing would occur anyway. So especially if you're running through baffle tanks, kind of like the ones I had pictured there, you have less opportunity for mixing between the injection point and start of distribution. So think about this for a second. If I'm injecting a really strong solution, especially during periods of lower flow rates, in order to not over-chlorinate, what my chemical feed pump is going to do is it's going to inject, and then it's going to have a big, long pause, because it has to stop injecting, otherwise it's going to over-chlorinate. Eventually, it will inject again. So what I'm going to have is running through my line and potentially through my contact system, I'm going to have really strong chlorine, followed by virtually no chlorine, followed by really strong chlorine again. And that's undesirable because it makes it very, very hard for you to get consistent test results. It also interferes with proper disinfection. Mixing helps alleviate that problem. So a static mixer, which is just like a section of pipe with some internal fins that creates turbulence in mixing. Sometimes people will put a water filter housing in there, just even without a cartridge in it, just a chamber that forces some level of mixing. Inside reservoirs, you can put mixers that stir the water. You could create some mixing by creating a vortex by the way the water comes into the tank, force it to kind of create a tornado effect at the top of the tank, which would create some mixing. There's some ways you can overcome this, but the best way to overcome it is to not have those big pauses and just inject a weaker solution more frequently. So instead of inject, long pause, inject, we have inject, short pause, inject, short pause, inject, short pause. And the shorter that pause is each time, the more consistency you will achieve in your chlorination. For most small systems, mixing 20 parts water to 1 part 12% sodium hypochlorite creates a really nice mix to achieve that consistent, even dosing and more even residual measuring. And certainly, make sure you use clean water to do your dilutions. So distilled water is best. Reverse osmosis water would be a decent substitute. Don't use raw water that might contain organics and iron and manganese and minerals. Even hardness minerals can cause problems inside your system by causing scale buildup in your solution tank and so on. So you want to use nice clean water to do your dilution. Okay, so some of the things that lead to low residual chlorine levels. First of all, where are you testing? You're going to have a big difference between chlorine residuals at the end of long distribution lines as opposed to immediately after your contact tanks. So you need to give some consideration to that. There is a minimum level to maintain that you should know immediately after your contact tanks. And prior to your first point of distribution. That would have been designed by the engineer or system designer when they designed your contact tanks. And you should definitely know that level. And then usually at the end of the distribution lines, you will need to maintain a specific residual determined by your health authority to ensure that you have that continuing disinfection through the whole distribution system. And those numbers will generally be different. So low residual could be caused by an increase in our chlorine demand. Something in our feed water conditions changed. We're pumping the same amount of chlorine in, but more of it is being used up interacting with organics or iron, etc. So our residual coming out the other end drops. We can compensate for that by improving our pretreatment, or we can up the level of chlorine we're injecting by turning our injection pump up. If you have a lot of fluctuations in feed water conditions, though, probably addressing the pretreatment will ultimately result in the most consistency in your water system. Obviously consider whether or not your chlorine solution is getting old and weak. And again, you can compensate for that by turning your chlorine pump up a little bit. Just remember when you put nice fresh chlorine in there, you're probably going to have to turn it back down a little bit. Try and keep it as fresh as possible. Sometimes though, you end up with a scenario where your pump just cannot keep up. So it's pumping literally as fast as it can, but in between signals that it's getting from your water meter, it can't complete the dose of chlorine before the next signal to inject more comes. So sometimes you can fix this problem by reducing your rate of dilution. You literally have to inject a stronger solution to get up to the level that you need to. This is not a really common problem, but it's more common in a system that's undergoing some level of expansion. So you used to have 10 homes in your mobile home park. Now you've added another 10 and you're serving 20. While now with that additional flow rate, you need a pump that has higher capacity. So some pumps you can increase the capacity by changing the peristaltic tubes in them. Some you might just have to replace the whole pump, or you could reduce your dilution and see if at a reduced dilution the pump can keep up. You can also have a similar problem where a system has such a low flow rate relative to the water meter capabilities that were installed. So I worked on a system in Saskatchewan where there was an old mining town that used to have several hundred homes on the system. The mine had closed. There were about 15 homes remaining. They had all this huge infrastructure that was designed for high flow rates, and they were trying to run very, very low flow rates through it. Well, they had to flow about 15 or 20 gallons of water just to even register on their water meter that water was moving. So it was very hard in very low flow conditions to even activate their chlorine pump because it wouldn't get a signal from the water meter. So if you're having a problem where your chlorine pump, you're running water and your chlorine pump isn't even trying to inject, you may want to look at your water meter as the problem. Seasonal changes can sometimes lead to low turnover in a storage reservoir. So think of a campground in the winter that goes from providing thousands of gallons a day to now providing a couple hundred gallons a day for a caretaker, but may still have the same size of reservoir. That reservoir is going to allow for so much contact time because of low turnover that the chlorine is going to dissipate. You can solve that by adding secondary chlorine injection right into the reservoir, boosting it as it drops. Or you can potentially just lower the reservoir level in the winter. The engineer or designer of your system can give you new calculations to run at a lower level and get basically a approval from the drinking water officer and public health engineer for those calculations, and then you just run your reservoir float or reservoir level control at a lower level during those periods. But too much contact time is actually a problem as well because the chlorine will dissipate. Certainly look for things like clogged injection points, foot valves, clogged tubing, and worn peristaltic tubes. If you have a peristaltic feed pump, you'll know what those tubes are. Those tubes get squished and they wear out over time. So they are a wear and tear item. The injection point is the point where the chlorine injects into your water pipe. That little point, especially if you have iron in your water, is very prone to getting deposits built up on the end of it or around it. So you should pull out that injection point and clean it periodically. The foot valve is the little one-way valve that sits at the bottom of your solution tank where you draw the chlorine solution. That little foot valve can get crystallized mineral deposits on it, especially if you're running high concentrations of chlorine or you're mixing it with water that has minerals in it. Clean that foot valve off so it, chlorine can pass through it readily into the tube, and check the tubing itself for any deposits. That tubing is incredibly cheap, and replacing it every year or so is well worth it to prevent problems. Difficulty in maintaining consistent residuals often is due to fluctuations in your chlorine demand, which we just talked about. If you're measuring your residuals using a chlorine analyzer with probes and sensors, those probes and sensors need to be cleaned and recalibrated often. kind of a little bit of the bane of chlorination systems for small small treatment plants, because they often require more maintenance than the value they provide. But if you do happen to have those parts, they're very expensive, and you want to keep them clean and lasting as long as possible and reading as accurately as possible. If they provide inaccurate feedback to your chlorine pump, you'll definitely get inaccurate results. Follow the manufacturer's recommendations for cleaning those probes and sensors, because they do vary by manufacturer. Again, consider whether or not you're diluting appropriately, because those long pauses between injections can throw off our consistency. You can consider adding a mixer to improve that mixing. And also consider where you're measuring from as well, and how it relates to the mixing. If you're measuring your concentration in between your chlorine pump and your contact tank, don't expect a high level of consistency at that point, especially if you're measuring really close to your injection point. It's going to be inconsistent if you haven't run it through some pipe or through a static mixer or into your contact tank. But if it's still inconsistent after your contact tanks, that's where you really have a significant problem that you want to address, related to either your chlorine demand, your dilution, etc., or dissipation. You've just got too much contact. Basically, we can't expect consistent results on the outlet if we don't have consistent results on the inlet. A consistent solution mixed well, and consistent chlorine demand. Okay, I'm just going to give you this is the last slide that I have, and then I can take some questions. But just a couple of other common problems that we see on chlorination systems. One is off-gassing, which results in a loss of priming of a pump. The stronger the solution you run, the more likely it is that you will have off-gassing. So again, dilution helps reduce off-gassing. Off-gassing basically is chlorine gas or other gases, carbon dioxide and so on, coming out of solution and forming air bubbles in your injection tube between the foot valve and the pump, and between the pump and the injection point. And that can cause the pump to lose prime and stop pumping. Peristaltic pumps tend to have a little bit less problem with this, but generally, if you can reduce your concentration and inject more frequently with less pauses and a weaker solution, you will reduce your risk of off-gassing. You can also reduce the length of tubing. You could have foot valve failure. Definitely clean your foot valve. Anything that is not allowing the solution into the line, deposits can cause this. And that foot valve has a little check valve, a one-way valve in it that prevents the solution, when the pump stops pumping, from falling back into the solution tank. If that valve has failed, you will definitely see more frequent loss of prime. So check that valve out and make sure it's operating correctly. Water should only flow through it in one direction, or chlorine. They're not very expensive to replace. And of course, make sure you're not running out of solution. If you run out of solution, you're going to start potentially drawing air in there, which will often cause a loss of prime. Disinfection byproducts and complaints about foul tastes or smell. The more consistent we can be in our injection, and the more consistent we are in terms of our chlorine demand in our raw water, the less buffers we need to provide to ensure that we're always injecting enough. So when we have high chlorine demand, or especially fluctuations in chlorine demand that are pretty wide, what we often end up doing is setting our chlorine pump on the setting that we need to address the worst case scenario. The rest of the time, we're actually over-chlorinating above what we really need to. And that can create these undesirable tastes and smells. So achieving consistency in our feed water with good pre-treatment is the best remedy for that. And it can also help us address disinfection byproducts, especially where that increase in chlorine demand is being caused by organic matter. So disinfection byproducts form when we add chlorine to water containing natural organics. It forms very, very harmful byproducts that we want to keep to an absolute minimum. So pre-treatment is super important for that. And if you're having a lot of byproduct formation, aim for improving the consistency of your pre-treatment to avoid that. Okay, let's open things up to some questions. And I can stay as late as we want here. I'm sure Natasha will have to leave at some point, but I can stay for a while longer. And as I said, we can also address questions via email, or you can send them into Natasha or me directly, and I'll make sure that they get answered. I do have one question here in the question bar that says, we have chlorine injection to precipitate iron, which reduces the iron and manganese levels, but there's still enough iron that we need to clean the quartz sleeve regularly. That is a common challenge associated with that form of iron treatment. I guess my question would be to determine what exists in between that chlorine injection point and your UV sterilizer. So what type of mechanical filtration might exist in between? At the very least, we would want to have some contact time, ideally 10 to 20 minutes after the point of injection of chlorine, and then some type of mechanical filtration, either cartridge filters, or ideally, or I guess next better would be a backwashable media filter like Nexand or Turbidex or Filtereg. And then even more ideally, an iron reduction media like Phylox or Catalox or Berm or something like that. Those iron removal medias enhance the oxidation further and can help complete that reaction that might not have fully completed by the time the water reaches your UV sleeve. If you don't have those in place, you could install something, one of those three measures. If you do have something in place, you could consider a measure that kind of ups the ante, go from cartridges to an iron filter media, or you could go from a 10 micron cartridge down to a 5 micron cartridge, and often you will see some improvement. There is also the possibility, though, that part of what you're seeing is related to some residual organic matter interacting with the iron. Usually the chlorination will break down that organic matter, which is really good, but it takes more time for that reaction. So if we have only a small amount of contact time, again, it might not be completing that before it gets to your UV sleeve. So adding more contact time could help reduce that effect. Anytime you have this sort of process in place to remove iron, I would still expect a more than average requirement for sleeve cleaning. If you're like at days or weeks, that's probably, you definitely could benefit from probably improving the treatment process. If you already have that full treatment process in place, probably something I'd review your water chemistry to see if we could figure out a root cause. If you're getting months, that might still be considered kind of normal when you have that kind of iron present.
Thanks, Grant. I think we have time for one more question here.
Okay.
So how about let's tackle this one right now. How about muriatic acid for cleaning UV quartz sleeves?
Not recommended. Muriatic acid would probably be the better choice of acids because some of the other acids have an organic base, like say citric acid. Muriatic acid is quite aggressive depending on the concentration that you're using. CLR is an acidic phosphoric acid type product, a little less aggressive. So we feel a little bit more comfortable because the aggressiveness does play a little bit of a role in the potential damage to the sleeve in the cleaning process. Organic acids would be worse because they could leave an organic residue that could absorb UV light. So it's not our recommendation. It's not the worst choice by any means. Be careful about the strength. Would probably be my biggest caution. And same with sulfuric acid, tends to be a little on the strong side of things.
Oh, okay. Thank you. Thank you. It's really good input. So due to our time constraints here, we're going to have to conclude the presentation. Grant, thank you very much for your really informative presentation. I always get a lot out of these presentations here.
So sorry for the short on question time, guys. Please reach out and I will make sure all your questions are answered.
Yes, I was just going to recommend that actually. If you reach out to Grant or the Online Help Center, we'll try and answer your questions. And we do apologize for not being able to answer all the questions today. I want to thank everybody for attending, and your CEU certificates will be automatically emailed to you today. Please remember to save them because we can't reissue them. Our next webinar is on November 19th, 2024 from 11 till 12:30 on the importance of drought-specific emergency response planning. I want to thank everybody today for attending. Thank you. Thanks again, Grant.
Yep, thanks everyone.